Let's step into the shoes of a medical detective today. One single piece of clinical data, a very specific handwritten chart, and we're going to decode it together. Think of this explainer as a forensic investigation. We've got the evidence right in front of us, and we're going to break down this complex graph to find out exactly how it points to a definitive clinical answer. But first, let's start with a cold open. Take a look at this quote: "Lupus anticoagulant present." This handwritten note, jotted down at the very top of the chart we're about to analyze, well, that's our final verdict. It is the conclusion to our mystery. And today, we're going to reverse engineer that exact conclusion. We know the destination, right? But our job right now is to figure out exactly how the raw data on the page gets us there. Okay, here is the complete, original handwritten medical chart. At first glance, I know, it just looks like a standard piece of graph paper with a sweeping curved line and some faint scribbles. But here's the thing. Every single mark on this page serves a highly specific diagnostic purpose. Our goal today is to act as medical detectives and figure out exactly how this specific visual data practically proves the diagnosis we just saw at the top. So, let's investigate the scene. We'll start with the testing grid. We're going to start on the left with the y-axis. It's labeled KCTS, which stands for Kaolin Clotting Time, measured in seconds. You can essentially think of this axis as a stopwatch. It's just measuring how long it takes for a blood clot to form in a given sample. So naturally, the higher up the axis you go, the longer that blood is taking to clot. Pretty straightforward. Now, shifting over to the x-axis along the bottom, this completely demystifies what kind of test we're actually looking at. If you read the bracketed rule directly from the chart, it spells it out for us. 0% equals 100% normal plasma and no test plasma. So this is what's called a mixing study. That text ensures we understand that the 0% mark on the far left, that is our healthy, completely normal baseline. As we move to the right along that axis, to 20%, 40%, 60%, we are slowly mixing more and more of our patient's test plasma into that healthy normal plasma. Which brings us to the number 72. This is our starting line. When there is absolutely 0% of the patient's plasma in the mix, meaning we are just looking at the 100% normal, healthy control plasma, the clotting time sits right around 72 seconds. What's really fascinating here is how the physical evidence backs this up. If you direct your eyes down to the faint handwritten notes near the bottom left of the graph, right at that 0% mark on the x-axis, you can actually see the number 72 scribbled right there by the technician. It's amazing. That anchors our baseline number directly to the clinical notes. So we've got our definitive starting point, 72 seconds for healthy blood to clot. Now we can actually trace the progression of the curve. Step 1 was our normal baseline, but look at step 2. As soon as we start moving right, introducing just 10 or 20% of the patient's test plasma, there's this incredibly steep, dramatic rise in the curve. The clotting time is just shooting up rapidly. Basically, a tiny bit of the patient's plasma is radically disrupting the normal clotting process. And then we hit step 3. Instead of continuing to shoot upward forever, the curve forms a very distinct plateau, settling into a highly specific pattern. That steep rise we just talked about, it eventually peaks and flattens out around the number 150 seconds. I really want to highlight this peak plateau point to emphasize the dramatic anomaly we're looking at here. I mean, compared to our healthy baseline of 72 seconds, the mixture containing the patient's plasma is taking more than double the time to clot. That is massive. And this brilliantly illustrates the actual shape of the anomaly. Look closely at exactly where the line stops rising. It hits that 150-second ceiling right around the 50 or 60% mark on the x-axis, and then it just flatlines completely across the right side of the graph. I want you to really note the specific shape this creates. It's a rapid initial climb that just abruptly turns into a long, flat, horizontal line. Closing the case, let's look at the type 1 classification. See, that specific shape, the rapid rise and the flat line, that's not just random data. It is actually a highly categorized medical response. Right in the middle of the chart, there is a printed box that literally says type 1, with an arrow pointing directly to the curve's plateau. This connects all the dots for us perfectly. The chart itself is illustrating how this distinct plateau shape is explicitly labeled as a type 1 pattern. In the world of KCT mixing studies, seeing a type 1 pattern is the exact definitive proof a clinician needs to confirm the presence of an inhibitor. It is the literal visual proof required to confidently write lupus anticoagulant present at the very top of the page. We did it! We successfully traced the evidence from the raw axes to the curve, all the way to the final diagnosis.
So, you have officially decoded a complex medical chart today. You've learned how a baseline is established, how mixing plasma reveals hidden anomalies, and how a very specific type 1 shape acts as a diagnostic fingerprint. But as our investigation comes to a close, it opens up a whole new set of questions. With the lupus anticoagulant now undeniably confirmed by this data, what are the next steps for this patient? How exactly does this delayed clotting time impact their everyday health? And what does this mean for their future medical care? Well, that is the fascinating mystery I'm going to leave you to ponder today.